Okay, so let's start now. So we will do this today because we have this circuit we stopped here yesterday, and this is adder subtractor circuit where we can use this circuit to add and to do the sub, right? So before that, I want to explain a little bit here how the add and the sub is performed in this circuit. Oh, all right. So if you look at here, this is n bit adder. So n bit means that can be any bits, 1 bit, 2 bit, 3 bit, 4 bit, 8 bit, 64 bit. All right, and we have one group of input here, x, and another group of input here, y. All right, but y is connected to XOR gate like this, and this is the sum output, and this is the carry output, and this is the Cin input. All right, so I explained this before we try to write the Verilog code for this one. All right, so why we have this XOR gate here is that all right, so hope you can see this is the all right. We learned yesterday that to do subtract, right? To do subtract, one of the input, for example, A minus B. So what actually we do is that A plus minus B, and this minus B is actually second complement number. All right. So and this is the concept that we want to implement in hardware. So we need to think of how to get this second complement for B. So the answer is that you do the complement, all right, you not B, and you plus 1, right? So what you can do is if you have the adder, for example, okay, so one input is A. So to get complement number, B, all right, second complement B, so this is B. So what you can do is you have the NOT gate for B, and then this C out you set to C in you set to 1. Then you can get complement B here, second complement B. All right, as C out. Okay, this is full adder. Okay, if you do this, means that A here, adder plus, and this is B bar, and you add 1 here. If I can explain here, all right. A, this is A, add, this is add, and this is here. One of the input is now B bar, and you add 1, right? You add 1 here. Okay, C in B bar plus 1 means that this is the second complement of B. All right, plus minus B, and this B of course in the form of second complement. All right, So that is the idea. But in this case, in this case, we use the XOR instead. Why we use XOR here? Because here we want to create an adder subtractor. Means that this circuit can be used as an adder or can be used as a subtractor. Alright, depend on this signal. If we use, if we do this, this circuit can only be a subtractor. Alright, so this is subtractor. So why we use XOR gate is that if you look at XOR, yeah, XOR, so we have MN, I use MN and F input. So we have 0, 0, 0, 1, 1, 0, 1, 1, and we have 0, 1, 1, 0, right? So when we look at the characteristic of the XOR gate, so we can see that if M here, if one of the input, for example M, equal to 0, so look at F. F will equal to one of the input, which is to the another input, which is N in this case. Alright, see? 0, 0, 1, 1. But if but if the input M is equal to 1, we can see that output F here is the complement number of the N input. Alright, see? If we have N here equal to 0, so F equal to 1, and if N here equal to 1, F equal to 0. Alright, so this is complement. So this is good. So because we can do, or we can have something like this, where we have an adder, alright, this is our full adder. Okay. Right. So we can have one input here is A, and we have XOR gate here, B, right, try to draw very carefully. Okay, XOR, one input is B here, and we have here, we have output here, and this one is connected to what we call the control input, controller. So let's name it as control first, control, and let's say this control is the same signal as this one. So let's see in it here. If control equal to 0, what is the output for this gate? Should be B, right? Should be B. Okay. So in this case, just imagine that here, if this one is 0, means that this one, now here this one is connect to control, right? If 0, and this one is B, for example, 0, so F here, the output here is equal to the input, another input here, B, right? So this should be B. Okay, if this is B, so what is the output here? Or what is the operation of this? Must be, yeah, S should be equal to A plus B. Means that if signal is 0, control is 0, so this circuit will perform the addition, the add, right? But if control equal to 1, so let's say we change the control to logic 1, and let's see what happens. If this is 1, so now if the control is 1, means that the output of this is the complement of this, right? So this should be B bar. And again, because this one is connected to this as well, C in of the full adder, so B bar plus with this one, so you have the second complement number. So if this is 1, so you will have the operation of S equal to A minus B, or in other words, A plus, because we use adder, minus B. Alright, so this is why, or explanation why we use this XOR gate instead of NOT gate. Because if you use NOT gate, that is means that you fix already that the circuit is the subtractor. Yeah. Okay. So that is the explanation of this circuit. Now we want to write the code. Yeah, the Verilog code for this circuit. Right. Of course, you need to open Quartus II. So right. So let's open Quartus II desktop. Okay. So if you have computer now, so you can try to do this together. Right, so this is my Quartus II. Okay. All right. So now what we want to do is this. Let's make it smaller so that we can. Okay. And we should have another one is this one. Okay, maybe that. Alright, hopefully you can see the screen. Okay, good. So now we want to create this circuit, and of course we need to have the n-bit adder first, or the 1-bit full adder. Alright, so you need to create the 1-bit full adder. So how to create 1-bit full adder? So again, you go to File, alright, and go to New Project Wizard. Click this, and you will be bring to this window, introduction window. Okay, just click Next, and then directory name, top level entity. So this is when you need to set your working directory or the folder that you want to save your project. Yeah. So in this case, we create a new one, and remember that if you uh, want to design using Quartus, so it is recommended to have a unique folder for each project. For example, this is a new project, so so we want to create the full header. So let's name this folder as FA, maybe FA2 because I have FA1 already, so I name it FA2 in this case. All right, so double click. And just select folder, and the name for the project is FA2 as well, and just click next here and add files. So because this is our first design and we don't want to add any other design to this this design yet, so we need to skip this step first. So just go next. And for the device, if you want to use the actual device, then you need to select the device. So the device that we have is the Cyclone 2, and the which one is, you can refer to the previous, to my previous tutorial. And for this case, because we want to do simulation only, so no need to select device. So let the computer to select the device automatically for us. So just click next here, and now EDA tools. So this we will do later after we have designed our full header. So just click next here, summary. Okay, finished, done. So we have our name of our design is FA2. You see the device is auto. So this is doesn't matter for now because we want to do the simulation. Want to see whether our design is working or not, right? Now we want to create the header. So go to new and select Verilog HDL file and click OK. So you will have this window. All right. Now we want to create the full header. So let's look at the full header. Where is the full header? Is it here? Yes, this is full header. We want to create this one, and as you see, this one we have the equation already, so we can model using the data flow modeling, right? So very easy. Just you need to have module, and the name is FA2, and what is the port? Yeah, the port for our module is X1, X, Y, C in, and let's change the name a little bit for this one. We change to this is this one. We try to change to X, Y, and this is C in, this is S, and this is C O, C out, right? Smaller, okay. All right, so we have the port is X, Y, and C in, and we have S, and we also have C out, CO, okay. And we need to specify our input. So this is the input, X, Y, and C in, all are 1-bit input, so it should be no problem. So the output is S and C out. Very easy. Okay, now we want to model using data flow modeling. So data flow modeling, we need to use keyword assign and write the equation. So the equation we have here, and make sure that the equation is correct. So this is correct for the full header. So for S, yeah, we have equal to X XOR Y XOR C in, okay, and assign C out, in our case C out here, not C0, CO. Okay, and we have this one, X and Y. Okay, so X, we use this X and Y, and this plus is O, yeah, or not plus, this is O, and X and C in, and the last one we O with Y and C in, Y and C in, done. And this is our 1-bit full adder. Okay, all right, can you follow? So now we can save our design, and of course it will save in this FA2 folder. Just click save, and save already, so we can synthesize our design and check whether we have any syntax error or not. So we can go to processing, start analysis and synthesis, or you just click this button. All right, simply click this button, synthesis, and right click. So your computer or the Quartus will start to not compile, it synthesize your design. So make sure that here the result is successful. Okay, and one warning here is doesn't matter, because if we look at the warning, this warning is about the license, and because we use the free license, so the parallel compilation is disabled. Means that the compilation is slower as compared to the paid version. Yeah, so it should be no problem. And now we have this already, so because our equation is correct, yeah, is design is very simple, so we can skip the simulation for this circuit. So we will use in our adder subtractor circuit. Right, so we can close this project and create a new one. All right, create a new one, and now the folder, the directory, we create a new one. All right, called add sub, maybe add sub. All right, and file, the name for the project also add sub. Okay, and click next, and file. Now here we want to use our previous full adder circuit or module in this add sub module. So we need to add the file, right? So here you need to add the file. But if later you miss this step, for example, you not add the file here, actually you can do that again in here. All right, you can assign later on. Okay, hold on, I have the message from the Google chat. All right, they can want to see the previous code for the okay, want to see the previous code. Yeah, hold on. Okay, so this is the previous code. All right, I open in Notepad because I don't want to go back from Quartus II. Okay, they can ask want to see the code. All right, so you can get the code now, or maybe I okay, I paste at the or in the chat room. All right, there you can copy and paste from there. Okay, get it good? The last function should be n. Ah, yeah. Yes, I can correct. So this is wrong. Okay, should be n. This is not O, should be n. Yes. Okay, so I can actually I can save here, and it will update the file. So no need to go back to that file in Quartus. Yeah. So just save here, and it will be updated automatically. Should be no problem. Okay, thank you, Adekan. Okay, any other question before we proceed? No question? No question? We proceed, yeah? Okay. So, here again, we want to add the our previous design to our new design here. So we need to add that previous design. So we will add here. Okay. So how to add? So just go to this button, click this button, and of course this is the design that we want to attach to this add submod design. So click open, and need to click this button, yeah, add, yeah, and make sure that the file is listed here. Okay, and then you can click next. Here you can just skip this step, click next, next, and click finish, and yes, you have the add sub module. All right, and now we want to write the code for the add sub module, and let's see, go to the add sub module. This is our add sub module. All right, so we want to do this, and we have the design here, what the adder in this block already, so should be no problem then. All right, and this is our design, right? So maybe I put somewhere here, make it smaller so that we can, okay, all right, because we still need this one as our reference. All right, now we want to write the code for this. Again, we need to create a new Verilog file. Go to new Verilog, click OK, and yes, module, and the name is add sub. And now what is our input and output? So we have x, we have y, but now x is not 1 bit anymore. So let's say our design is 4 bit. All right, we limit to 4 bit, or maybe 8 bit. I think better at 8 bit, so we can simulate later on. We can see. Okay, so let's say we have x, we have y, and we have this C, let's name it C out, CO, and this one S, so name is just S, and we have one signal here. The name is add sub control, so name should be different from this, maybe add sub. All right, something like that. So we have input. All right, and our input is X and Y, yeah, 8 bit, so we can have 7 to 0, X and Y, 8 bit, and we have 1 bit input here. So again, input 1 bit, and we have 8 bit output. This is the sum S, and we have 1 output, 1 bit output, which is CO, output CO. Okay, done. And also we have this gate. Yeah? So this gate we can create using data flow modeling. All right, or we can create using structural modeling. All right, gate instantiation. Right. So in this case, I prefer to use the data flow modeling. But again, if we want to use the data flow modeling, so we need to have this signal. All right. So this signal. Okay. So this signal, let's name this signal as what to use. So maybe we use A. All right. So name this signal as A0, A1 until AN-1. Right. We name it as A. So in our code, because this signal is not an input and output, yeah. So we need to set or declare this signal as wire, right? And this is 8 bit as well, right? So wire, and the size is 8 bit, and the name is A. All right. Now we can create A0, signal A0. So how to create A0? So you can use assign. A0 is equal to Y0 XOR this add sub signal, right? This one. So you get A0, right? And then to get A1, you can just copy and paste, right? A1, Y1. And you can use the for loop also here to create this. But if you want to use for loop, you need to use behavioral modeling. And you do need to use always block. Right? In this case, let's use this data flow modeling. Right? So we have so this is good about programming is you can always copy and paste like this, right? And the pattern is just repeated. So we can have 2, 3, 4, 5, 6, and the last one is 7, and this is the same. So it should be 2, 3, 4, 5, 6, and 7. All right. So we have all the A signal from A0 to A7, A0 to A7, where A0 is Y0, X or X sub signal. All right. And A1 is Y1, X or X sub as well. So this is the same signal, so it should be no problem. Now we have the signal for this already, so we can instantiate our full adder in this design. So how to instantiate? Very easy. So the design that we want to use in this case is FA2, yeah, full adder 2. And let's say the first module, because we have 8 bit, yeah, remember, so you will have 8 module inside here, actually 8, yeah, FA2, right? So let's name the first one as module 0. All right, so let's say this is module M0, and we need to do the connection. All right, so the connection is, we need to refer to the to this to the FA2 module. So the first now an FA2 module, the first port is X, X. So in this case, so should be connected to X0, right? M0 should be connected to X0. Okay, so in this case, so we just connect to X0 and connect to here Y. Now our Y is here, F2 here. This is if I make it bigger, all right, so you have X, you have Y. Okay, of course this X is connected to the X0 here, and this Y is connected to A0, yeah, not Y0. This is connected to A0. Okay, so in this case you need to have A0 here that connected to this Y. And what about Cin? Cin in this case is this signal, which is add sub signal, right? That connect to this FA2. Okay, so which is this signal. So we have that. And the next one is S. Of course, this is S0. So just S0. And C is here. Oh, we need another signal here. We don't specify yet in our code. So we need to specify maybe, so we have C0 until C, how many? C0 is here already, so this is C1. So we just name this signal as C1. Okay, C1 until C6, correct? Yeah, so I draw again, try to, so that you can, so we have 8 full header here. Hold on. 8, 1, 2, 2, 4. So I will have 8 of them. Okay, 8 FA2. Right. So the name for this one, we call it C1. This is C2. C2, C3, C4, C5, C6, and the last one is C7. This one we have name already, which is CO, right? This one we have already CO. So until C7. Yeah, so we need that one. This signal. So this signal again need to declare as a wire. So let's do that. So here wire we have 7 to 1 only, start from 1, and the name is C. Alright, should be good. So this one should be C1, right? So this one should be C1, yeah. So here should be C1. Now the first, this is our first FA2. And now we want to have the second one. The second one, maybe I can just copy this. Alright, because the it's almost the same, and FA2, okay, the submodule is the same, and but the name for this one should be M1. Cannot be the same with the first one, because in here this is M0, and this one should be M1, and this one should be M3, and so on, right? So what is inside? So this should be X1, this should be A1, this one, all right, this one is the input for this C in for this one should be C1, right? So here we have C1, okay, and S should be S1, right? The output for this one should be S1, and the output, the C out for this one should be C2, in this case C2. All right, and the best thing is that after this, this pattern will be repeated, except that the number is different, right? So we can have M2 here, and this should be 2, this should be 2, this should be 2, this should be 2, and this should be 3. And this is repeated. So we can have again. So this is 3, this is 3, this is 3, 3, 3, and this should be 4. Okay. M4, this should be 4, this one should be 4, this one should be 4, 4, and 5, and right, the rest should be the same until we have X7, right? And the output should be C out. That's it. M5. Alright, you can do this together. This is the last one. 7, 7, 7, 7, 7. Is it C7 here? C8 here? No, right? Because the last one, this module, the last one should be CO, right? So it should be CO. Okay, this is CO. 1, 2, 3, 4, 5, 6, 7, 8. All right. So we have 8-bit and done. Any other signal that we missed? All right, here we have already this this I think should be okay now, and we can have n module. No semicolon. Okay, hope you can follow. Now we need to synthesize our design, and let's see any problem with the design. So first thing first is we need to save, right? So save the design, save, right? And synthesize here. Looks good. Nothing wrong with the design. No error. Alright, but if you write your code, if you get the error that and it's actually good, yeah, it's actually good because um, it's it's normal, right? When we write the code, we sometimes we miss type or miss a signal or what, yeah, and we get the error message, and that error message actually you can learn what you did wrong. All right, you can read the message and try to figure out, try to debug your code. All right, so you learn from mistake, learn from error, so that will help you understand the cost very well actually. All right. uh, all right, and in this case, because I do this a lot of time already, so the error is minimum, all right. But in your case, if you get error, don't worry. All right, try to look at the error or warning that you have and try to read and understand what is the error about, and try to figure out and look for the mistake, and that will be a good lesson for you actually. All right. So when we look at this here, see, when we synthesize our design. So in the this the top level is at sub, but inside here we have many same module. All right, M0, M1, M2, M3 until M7. So this module is actually inside this at sub module. All right. Okay, now we want to simulate our design. So there are two options. First one is to use the what we call this uh, the University program VWF. So this is a waveform editor that you can put uh, the input vector, all right, the combination of input in the form of waveform, and when you run the simulation, it will give you the waveform of the output. So this is integrated in Quartus for the university student to learn Quartus. But in the industry, normally they use what they call a uh, test bench, where we, instead of drawing uh, the waveform, but we use the script or the language, the text, to to create the waveform. All right, in the form of language. All right, so I will show you that. Okay, so instead of doing this, we will try to write the test bench here. So how to do that? Just go to the new and create a new another Verilog file, and this is called the testbed file. Okay, so what we will do after this is this. So when we yeah um, okay, so what we will do after this is something like this. Okay, so we have our design now is in the box like this, and the name is the add sub module. Right, so our design now will be called design under test, or in short is DUT. All right, and we will have the input where we have this is the input X, and we have Y input, and we also has the add sub signal, right? Add sub, and here we have S, and here we have CR, right? And when we want to do simulation, we need to create another module, right, called test bench, right? Okay, so let's say this is the test bench. And we, of course, in the test pen, we need to have input as well. So let's say the name is also the X and Y, and this is the same. This is the same connected to this. Yes, this one is also C out. Okay, and this, for example, we call it test pen GB. Okay, right. So we want to do this. So what we need to do is we need to create a new Verilog code. All right. Again, create a Verilog code here. So you have new Verilog code. All right, and try to write the code. So to write the test bed, first thing is you need to define the time scale, because we want to do simulation. All right, so we need to have the time, what we call it, time scale. So just write time scale. Okay, so and the time unit that we want to use. So in this case, maybe we use 1 nanosecond for 1 unit time, and the precision is 1 nanosecond. Also, precision means that the simulation tools will evaluate the output every 1 nanosecond. All right. So if you write 10 nanosecond here, for example, 10 nanosecond here means that your time unit is 10 nanosecond. When you write time later on, 2, for example, that means 20 nanosecond. All right. So in this case, we use the same 10 nanosecond, 1 nanosecond time unit and 1 nanosecond precision. All right. And now we need to have module also. All right. So this one is also the module. Let's name our module as at sub testbed. All right. And don't need to list the port, just do this. Okay. And in testbed, this signal must be declared as rec. This X and Y must be declared as rec, and not input and output. All right. So this you need to declare as rec. This one you need to declare as rec. This one also need to declare as rec. And the output need to be declared as wire in testbed. So it's different from the module here, where the input is input, output. Yeah, but in testbed, this one is right. So in this case, so we can just go back to this. So here instead of input, so maybe we can copy this, right? Copy this. So instead of input, now we change to rack and change this to rack. Okay, and here is the output, and again we need to declare as wire, and this one also wire. Okay, so now we're done with this. Alright, so now what we need to do is to instantiate this our add sub module in this testbed module. Alright, so how to do that? So just like we instantiate our previous design, so just name the module that we want to instantiate, which is add sub. Alright, this module add sub. The name for this is, maybe we call it TB or M0 or whatever you want to name it, and the list of the port. Alright, so it should be the same orientation with this one, the same sequence as this one. So maybe we can use this one, just copy and paste here. And in Quartus, it is recommended to use the port connection syntax. So if you look back to the notes, so here chapter 2, hold on, we go to chapter 2. Alright, when we look at chapter 2, when we do hierarchical mode design methodology, so there are two ways of port connection. First, we call it positional port connection. So just now we use the positional port connection. But in testbed, it is recommended to use port connection syntax. Use this syntax. All right. So for example, this one dot A is means that this one is connect to this A, So in our case now is this. All right. So the name is the same, so it's easy. So just dot X, and it is connected to X, and dot Y is connected to Y, dot CO is connected to CO, dot S is connected to S, and the last one is dot add sub is connected to add sub as well. Done. Alright, so now we instantiate our add sub module already in the testbed. So we have this already. Now what we want to do is to tell the simulator that we want to create the waveform for that. So the syntax is to use this $sign, but before that we need to use the initial block, initial, and we need to have begin. All right, and we want to monitor. Okay, we want to see. Okay, in the bracket, and we want to see what we want to see, time. Okay, time, and in means that the x-axis is time, and we want to look at the y-axis what we want to look at. So in this case we want to look at x, y, co, s, and at sub, right? So want to look all of that. So maybe I just copy this and put here, and of course before that you need to have this, yeah, this, and finish. And in X, the data format that we want to look at, maybe we want to look at put it binary first. All right, %v means that binary, right? This one also in binary, this one also in binary, this one also in binary, and this one also in binary, and we need to map to the port. Okay, so how to map to the port? Again, the port is this one, so just copy this again, copy, and just put all here and finish. Means that at this x at y-axis is actually x, port x. This y is actually port y, and so on. Okay, so we have that for the monitor, and n, and now we want to create the stimulus or the vector, input vector to our design. All right, so we need to have again initial, begin, and now at time 0, what is this? What is the time 0? Yeah, time 0 mean here when I write this, yeah, this means time 0, and time 0 means that because our time scale is 1 nanosecond here, is that this is 0 nanosecond. All right, so time 0, our input will be x equal to maybe we use decimal. All right, x equal to 5, y equal to 3, and what else we want? CO is the output, right? So this one is the one that we want to observe, and add sub, maybe we want to do this the add, yeah. So the add sub must be 0 first, yeah. This means we do the add, yeah. So this is a add operation. All right, add operation. Now, for example, at time 20 nanosecond, I write 20. All right, 20 here means that this is 20 nanosecond because our time scale is 1 nanosecond. Unit time is 1 nanosecond. 20 means that 20 multiplied by 1, so we have 20 nanosecond. So at 20 nanosecond, maybe we want to change the operation, change the value of x to, for example, this is 3, this is 1, and this is still sub, and another still add, and another 20 nanosecond. I change again to this one is 5, this one is 2, but now I want to have a subtract operation, so I change this signal to 1. All right, and again 20, I want to sub again, maybe this one 5 sub 5, so we should have 0, and again maybe 5 maybe this one is 8, 2, and so on and so forth. So this is sub operation. Sub, right? This is sub. This is sub. And then we want to finish the simulation after 20 after this 20 nanosecond after this, so we can use stop. Okay, so the time here is accumulated. For example, if we write 0, 20 here means that 20 nanosecond, and here another 20 nanosecond means that the time now is 40 nanosecond. 20 plus 20 is 40, and this one is plus 20, so this is at 60 nanosecond, this is at 80 nanosecond, and at 100 nanosecond we stop. Yeah, so this is the time is accumulated. All right, so we can end our simulation here, and module. All right, so we can have something like this. Before I share this code with you, let's try to check whether we have any syntax error or not. All right, we save the file first, and the name is what is the name? At sub tb. So at tb, save. Okay, looks like good. All right, so no error. And if no error, we want to try to simulate our design now. Before that, I share this code with you so that you can okay. Right, so now we want to simulate our design. So to do simulation, yeah, in Quartus, or to run your test bench, what you need to do is you need to do some settings before we you can do simulation. So, and the simulation now is called the functional simulation, where we only look at the function of our design. We not look at the timing yet. Means that we ignore the delay factor in this functional simulation. Later, when we want to do timing simulation, we need to compile the design based on the target device first, so that we can look at the timing, how fast is our design, and so on and so forth. All right. For now, we want to do a functional simulation. So what we can do is, all right, so to do the setting, so we need to go to assignment, go to setting, and here, yeah, choose model sim Altera, right, and compile test bench, because we want to use the test bench. So click this, enable this, and click test benches. And here we click new, and name, write the name of our test bed, and make sure that it is the same as your test bed file, which is in this case is add sub tb. Okay, and here we need to add the file. So to add the file, just click this and select our testbed file, click open and add. Now make sure that the file is listed here and click OK. So this is our testbed. Click OK. Just click apply here and click OK. Means that the setting is done. Alright, now we are ready to do simulation. So to do simulation, you can click this button. We call it RTL simulation, or in the previous Altera Quartus version, we call it functional simulation. So and this another one is the gate level simulation or timing simulation. All right, we will do this maybe in chapter chapter 5 or chapter 6. Yeah? And in this case, we do RTL simulation. So click this, and now the modern sim software will be executed. All right. So wait for a while to invoke the modern sim, and the speed of the simulation will depend strongly on your computer speed. If your computer is slow, then the simulation will be slower as compared to faster computer. All right. So this is the output. Maybe okay, we can make it. Maybe we use decimal number instead of binary. Easy uh, to interpret. All right. So radix, you can change the radix from binary to decimal or hexadecimal here. All right. So we can change to decimal. So and maybe we zoom in full format. All right. So if you cannot see here, maybe I try to capture this. Okay, so that you can see it clearly, or maybe again I try to zoom zoom out. Okay, I think this better. Right. Okay, so I have these. Can I zoom? Yes. All right, so that you can see clearly here. Okay, let's see what is our output. So for the first, I actually need to have the time scale, right? So the time scale is here. So this is actually 10, 20 nanosecond, yeah? 20, this is 50 nanosecond, you see? This is 40 nanosecond. So it will change at 20 nanosecond, yeah? So this is actually 20 nanosecond. Yes. This is 20. Right? So this is 20 nanosecond. And this is 40 nanosecond. Okay, so as what we have done, we at 20 nanosecond, all right? So this is adding or addition operation. So input x here, this is y, x 5 plus 3, we have 8. So correct, yeah, the output is correct. And here, 3 plus 1 is 4. And now we change the add sub signal to from 0 to 1, means that from here 40 nanosecond, the operation is now subtraction. All right, so let's see, 5 minus 2, we have 3. Okay, so this is correct. 5, this is still 5. 5 minus 5, we have 0. 8 minus 2, we have 6. So this most probably that indicate that most probably our design is correct, right? But we need more, actually more test vector. This is too too few, too small. The number for test vector is too small. All right, but it's look good. It's look good for now. It's look good because we have all the result here is correct. All right. Okay, so that is how we do the design, and we verify the design, so that we know exactly that our design is correct or not. All right. Okay, so that is I think for this tutorial. I hope that you understand what I try to deliver. Okay.